we derived the very important approximate accumulation function, so I want to talk about that. And your homework over the weekend will have lots of dissecting that and using that and understanding that formula, so let's just talk about that. And I want to talk about the big picture of it because that's the most important thing. Then the details are less important. They are important. You need to know the details, but the details don't matter if you don't know the big picture. So we want to know the big picture. And here's the general structure of it. So this is kind of the general structure of it. And so it's a sum of two things. So let's start by... Oh, you're off the hook. I forgot my attendance list, so I'll have to bring that Tuesday. But okay, so I'll just call on you by color of your shirt. How about that? All right, so talk to the person next to you for 1 minute. This basically, the accumulation function is the sum of two things. So what is the first thing in the sum? What is the second thing in the sum? Go, 30 seconds. Okay. Here we go. All right, so tell me. I put a circle around the first sum. What is the meaning of that first thing I circled? Yeah? No? Yeah. In the red shirt. Yeah.
The sum of the completed intervals.
Okay, so it's a sum having to do with the completed intervals, but the sums of what? So completed intervals are just objects. So the sums of what values related to the completed intervals? Okay, how about right here, in the light blue shirt? The sum of what? The sum of the changes. Changes in y, right? Or whatever our quantity is. And we have this rate function. That rate function is for a quantity. So it's the sum of the changes in that quantity due to the completed intervals. Okay? And then what about, I'm going to put a rectangle around that one. The rectangle. Tell me, right here. What does that mean when I put a rectangle around?
It's the accumulation in the current interval.
He said it's the accumulation in the current interval. Agree or disagree? Yeah, it's the amount of accumulation in the current interval up to x. Okay? So let's talk about that. This thing is primarily about two key principles that we've been hammering for the last month. We've been working so hard on these. And that first principle is this. That the change in the dependent variable is a constant rate times the change in the independent variable. Otherwise known as what? You all should know how we have expressed this. dy equals mdx. mdx. Where does this show up in our accumulation function a? Where does it show up? In the second part. Does it show up in the first part? Yes, it shows up everywhere, right? It shows up everywhere. Every completed interval is calculated by mdx, the rate times the change in x. Every completed interval, and then that's going to sum them all up. And then also, we see the exact same principles, and then we're going to sum up the accumulation in the current interval. And that's, again, mdx. So it's a bunch of mdx's summed together for the completed intervals, plus the mdx for the current interval. Okay, what's different? In the completed intervals, the change in x is a whole moment, delta x. In the current interval, is it less or more than a moment? Less. Dx varies through the moment, right? Dx varies through the moment. So for any given current value of x, dx will be less than delta x. So that little amount of change in the current interval will be for a change in x something less than delta x. But the whole thing is just summing up a bunch of these. That's the big picture of this a function. We're just summing up a bunch of mdx's. And as we work on the details, we want to never lose sight of that. Okay? Number 2. Final value of dependent variable is the initial value of the dependent variable plus the change in the dependent variable. Otherwise known as?
Y final equals Y initial plus boundary.
Plus dy. So a final value of a quantity,
Sorry.
you almost had it. It was great. Final value of the quantity is the initial value of the quantity plus a change in that quantity. So where does this show up? Where does y initial show up in this formula up here? So it changes. Y initial changes, and it's equal to? It's the total accumulation for the completed intervals. We can think of that at any given point, we can think of the total accumulation of the completed intervals as some initial value of accumulation. And then the dy is then what's accumulating in the current interval. So y initial is like everything that's accumulated in the completed intervals, and then the dy is what's accumulating, right? Dy is dx is changing through the current interval, so dy is adding on to that y initial. So we have accumulation within the current interval, and that's the change that we're adding to all the accumulation we had before for the completed intervals, y initial. Okay, so like I said, we are going to have to know the details of the formula. We'll talk about those in a second. But it doesn't make any sense to know those details without knowing the big picture, the structure, and the overall meaning of what's going on. Okay? So let's talk about the details. The first detail is how many completed intervals we have. J equals 1, 2, 1, up until the total number of completed intervals. And on Tuesday, we derived how to get the total number of completed intervals. And that was the floor of x minus a over delta x. So we took about 5 or 10 minutes to work through where that formula came from. Okay? Then the next question is, how do we get each rate? How do we get the rate for the jth interval? What x value do we plug in to get the rate, the constant rate for the jth interval? And we did that as well. And we found out that we're going to use the x value at the left side of the jth interval, and that's calculated by that. So this is the x value at the left side of the jth interval. Is that left of x? That is not left of x. So this is, it's similar, but it's the x value at the left side of every completed interval. You have the jth interval, which are the completed intervals. Okay? So that we said before, sums up the total accumulation from the completed intervals as m dx plus m dx plus m dx, right? Every time j advances to the next value, you get the next m dx for that next completed interval. And we sum all those up. Okay, so now this is for the current interval. What value of x do we plug into r to get the rate for the current interval? That's left x. So left x is specifically the x value at the left side of what? The current interval. It's the one x value that's the left side of the current interval, not a left side of a completed interval. Okay? And then we need dx, and we need that in terms of x. So we saw that was pretty easy. If x is the final, left x is the initial value of x in the current interval, then dx is just going to be x minus left x. That's how far we have progressed into the current interval, dx. Okay, so any questions on the accumulation function? Again, always keeping the big picture in mind. When you're digging into the details of this, you can't lose sight of the big picture, which I did just a couple minutes ago. Okay, so let's do an example. We can go ahead and hand out the. Did I give you all of them? Oh, you're the best. All right. So we're going to look at an example. So this hopefully will help. What do I have? I have a truck, and it has a load of sand on it. And we're gonna start tilting the truck bed back so that the sand is unloaded onto the ground or a scale. Think of it on a scale. And so what I'm showing you is the rate of change of weight as a function of time. So the rate of change of weight is in hundreds of pounds per second. So if you look at the 2 on the y-axis over there, that's 200 pounds per second. Okay? And then as a function of the time since the first little bit of sand hit the scale. And so that's the static function you have on your handouts. Okay? So we are going to kind of walk through this progression up. So we know how fast a quantity is changing at every moment, and we want to know how much of it we have at every moment. So we're gonna be working through that whole kind of that progression, and then also getting into the details of the A function, right? So the approximate accumulation function. Where does that fit into the picture? And let's kind of dig into that in this particular example. Okay, so I think you can just start on the questions on the worksheet. Okay? Okay, so what are the coordinates of this point right here? Exact coordinates, right? That one right there. Let's write them coordinates. X coordinate is 1.2 seconds. Y coordinate expressed exactly. R sub W of 1.2. Now we're going to use that rate, R sub W of 1.2, to be the constant rate for that entire interval. And that's what I'm showing with the little blue segment, right? So we're going to use that constant rate, that rate of R sub W of 1.2 to be the constant rate for that whole interval. I'll stop it. And that's showing this right here. And we're going to do that for every interval, and in doing so, we create what kind of function? Approximate rate of change function. The blue one is the approximate rate. So then what I meant was, over here, where would we look for the value of that? Where would we look for the value of that rate for that point? The y-axis. So it's about, what, 4.2. It's about 4.2, but exactly, it would be, what's the exact value of that? R sub W of 1.2. Right there on the y-axis. Okay, before we go on to number 4, I want to talk about why does this rate function make sense in this situation? I should have said that in the setup. Why does this rate function, why does it make sense in the setup? Imagine we've got the truck, and we're gonna tilt the bed back, and then the sand is gonna slide out onto the scale. So can you explain why does this rate function make sense for that situation? Yeah, please.
Because when you initially dump the sand,
Okay.
it's not all going to come out right away. It's going to start coming out, and then about halfway through, like the bulk of it is going to fall out.
Right.
And at the end, less and less and less.
Did you hear that? So the rate at the beginning it'll be a low rate because sand will just be trickling off the bed. But then when it gets up to a certain angle, the truck bed, then like I said, the bulk of it'll come out fast. And then at the end, then there'll be just a little left, and it will slide off the truck in a small amount per second. So it just comes off slowly, and then quickly in the middle, and then slowly again. That's what that rate function is showing. Okay, so it should make sense in the scenario. Okay, so now we've got our approximate accumulation function, and just by what you know about constant rates, and you've got this approximate rate function, the one that's colored blue there. Can we just make a rough sketch of the approximate accumulation function? Can you make a rough sketch of the approximate accumulation function based on the approximate rate function? That's number 4. Go, see if you can do it. So think about it. What will that look like? What will the approximate rate function look like? We're accumulating at constant rates. If we're doing the approximate accumulation function, we're accumulating at constant rates. So every 0.3 seconds, what happens to the amount of sand, the weight of sand? It's going to increase. It's just going to increase at different rates. So if it increases at a low rate to start with, what will that look like? Increases, so the accumulation starts at how much? At 0 seconds, how much sand is accumulated on the scale? 0. So at a low rate, what will that mean for the accumulation graph? It accumulates at a low rate. It's going to be a shallow, right? It's going to be a shallow increase. And then in the next 0.3 seconds, it's going to keep increasing, but more in that 0.3 seconds, right? It's going to increase more than it increased before, starting from the place where we were. This is how you can think of it. And then what happens at the end? Does the weight start going down? Does the weight start going down at the end? No, it's still accumulating just at a lower rate at the end, right? So it's still going up, just at a slower rate. So lots of you had decent sketches. Lots of you had good ones. So now we want to dig into. All right, so let's answer question 5. Go do question 5, and then we'll do 6 together. Okay, then we'll do 6 together. So just question 5. This is on the exam. Let's all get this right on the exam. This is on the exam. This exact question. We're going to get it right. Okay, we got to get this. Okay, here we go. I hope you finished by now. So, in the black tank top. Back there, yep. What was the first function in the progression of functions? What did you say? He wants exact rate of change. Yes or no? Yes. We started with, I just showed you, what did I show you first? I told you this is how the rate that the weight of sand is coming off the truck onto the scale. That was first. That's number one. Number two, you guys drew the approximate rate of change function. We can't make any progress towards accumulation without constant rate of change. So we make a new function that's pretending to be the exact rate, but based on constant rates. So do you see how that blue step function is trying to be like the red one? But with constant rates, we can actually start calculating some values of change in weight and build the accumulation function. So we start with exact rate of change. Then we build a approximate rate of change function. And then what is next? How about here in the striped shirt? Right here. What's the third? Approximate accumulation function. Yes or no? Yes. So I had you sketch. Based on the approximate rate, I had you sketch an approximate accumulation function. And then finally, our goal in the whole process is what? Here in the green and brown striped shirt right here. What's our goal in the whole process? Function number 4. Not sure. Okay? How about in the corner there, in the black shirt? She said the exact accumulation? You got it. Right. 4 for 4. Okay, so I want you to look at the approximate accumulation, the approximate rate, and the approximate accumulation, and just make a prediction about the exact accumulation function. Where will it be? How will it relate to our approximate accumulation function? So what would you expect about the exact accumulation function compared to the approximate accumulation function based on our approximate rate function? So, to be more specific, will the exact accumulation be kind of right on top of that approximate accumulation? Will it have y values of weight less than that approximate accumulation, or will it have y values of weight greater than that approximation? Is that a hand or stretch? Stretching, okay. So what about in the first half? Up till 1 second. This is an underestimate. So the actual accumulation will have greater y values. Will be above it. Okay? So then in the second half, then will the accumulation function be below it? You're shaking your head.
Well, yeah, because now we're overestimating the second half, so it's above it and below it.
Okay, so there's a deficit has arisen, right? So by the time we get to 1 second, we're a significant amount too low. The actual accumulation function will be higher. So what will happen? Will it automatically, the exact accumulation, now jump lower? No, it's gonna make up the deficit, right? It's gonna start making up the deficit. So it will stay higher, but they will kind of converge. Does that make sense? Let me just show you. At the right moment. So does this make sense? So your prediction was correct. The actual accumulation is higher. Why? Because the red rate graph is predominantly showing greater rates than our approximate rates to start, right? But then in the second half, our approximate rates are higher, so, but there's already this deficit that's, by 1 second, we have this amount that we're way too far under, but then it will start catching up. Then it will start catching up again because the approximate rates are greater than the actual rate function. So by the end, it kind of balances out. The fact that the first half, we were approximating too low, and the second half, we're approximating too high. So by the end, it kind of has balanced out, and we are back at the close to the exact accumulation. So the question is, where in the heck does this thing come from? So where did I get that? Okay, where did I get that? So we're getting there. But before we do that, we want to dig into the approximate accumulation function, specifically at, what did I say? Let the current value of x be 1.4. Okay, here I am. The current value of x is 1.4. So we want to figure out how is a of 1.4 shown on this graph, on the approximate accumulation graph? A of 1.4, where do we see that on this graph over here? What about this visual right here is showing the value of a of 1.4? How about in the orange shirt? What do you think? The y-axis for what? Are you looking at this point? And then you're just going over here? How did I do? Is that mostly straight? So, right there, he's saying that's the value of a of 1.4. And what does that value of a of 1.4 mean? What does that mean in this situation? The approximate total weight? Accumulated weight? Yeah, the total accumulated weight at 1.4 seconds would be the y value on this right graph, right? Because it's the accumulation graph. So that's the total accumulated weight, and it looks like about 350 pounds. Pretty close to 350 pounds. So how does our big accumulation function come up with that value around this a of 1.4? So that's what I've got down below. So first, for a of 1.4, we want to do that. How does it calculate the number of completed intervals? Can I get both on the screen at the same time? Okay, that'll have to do. So what's our calculation of the number of completed intervals if we're at x is 1.4 seconds? Do you remember how it first gets the number of complete intervals? Because that's going to be how many terms we have in that summation notation, right? The number of terms in the summation notation is going to depend on how many completed intervals have gone by. So how does it calculate that number of completed intervals? Who remembers? All right, what is x? 1.4 minus a, which is 0 over 0.3, and then truncate, take the floor. So this is our x minus a over delta x. And that's going to give it, and then truncate that's going to give us the number of completed intervals, which is how many? At 1.4. We can just look at the graph. So instead of, how many completed intervals have gone by? I heard 3 and I heard 4. 4 completed intervals. Here's 1, 0 to 0.3, 0.3 to 0.6, 0.6 to 0.9, 0.9 to 1.2. 4 have gone by. So if you do that math, put that in GC, that will give us 4. By the time x is 1.4 seconds, 4 completed intervals have gone by. What's the value of left of x? What is the value of left of x if for the left of 1.4? What's left of 1.4? Right, it's the x value. It's the x value at the left side of the current interval only. Okay? What's the value of dx? Good, 0.2. How far we've gone in the current interval? So we said there are 4 completed intervals. So J is going to start at 1, and it's going to march up. 1, 2, and where's it going to stop? So put a vertical line like this. J is going to start at 1, and then it's going to be 2, and what's the last value it's going to be? J. Nope, J is, so, I need to have it on the screen here. Let's show it. What does it do? Look, hold on. J equals 1, 2, the number of completed intervals, which is how many? 4. So we're going to have J equals 1, then we're going to have J equals 2, and then it's going to do J equals 3, and then it's going to do J equals 4, and that's the last completed interval. So J is going to cycle through the 4 completed intervals by taking the values 1, 2, 3, and 4. What does this? Remember what this was. This is the x value at the left side of the current interval. Right? Look at, so it's the input value or the argument into the rate function. Okay, so in the first interval, it's going to be 0 plus J minus 1 is 0 delta x equals 0. Does that make sense? The left x value of the first interval is 0. Do you see it? Okay, second, let me move these over so we have more room. Second interval. So now we're getting into the guts of how this function works. Second interval, it's going to be A, so 0 plus J minus 1 is 1 times delta x is 0.3 equals 0.6. Is that right? No, 0.3. And what is that? That's the x value at the left side of the second interval. Third interval. It's going to calculate. Oh, I should go down this way. Anyway, third interval. 0 plus J minus 1 times delta x gives us a value of is 0.6, the left side of the third interval. X equals 0.6. Yes, it is. And then the fourth interval. A equals 0 plus, how many J minus 1 is? 3.3. So the left side of the fourth interval is x equals 0.9 seconds. Okay, we're going to do the partial interval later. Okay, so here we go. So now we want the rate. What does the formula do? In that first part, it takes the rates at these x values. What is the rate at 0? So the rate at 0, right? So it's gonna plug that a plus j minus 1 delta x into the rate function. So let's estimate these rates now from the y-axis. What would your estimate of R0 be? I heard 0.2. 0.25? 0.25 it is. What's the units on that? 100 pounds per second. So what is that? That's 25 pounds per second. That's 25 pounds per second. It would be 0.25, 100 pounds per second. Okay? Then it's going to take this and put it into, so now J is 2. Now let's do the first interval first. Let's do the whole thing for the first interval first. The left side x value is 0. The rate is 0.25. And then what does it do? It takes the rate times delta x, which is? It takes the rate times delta x. So 0.25 times 0.3 is what? 0. Help me out. 0.3 times 0.725? What is it? 0.7. Is that right? So do you see how when j equals 1, that accumulation function that you see over there on the right on your paper, we just worked through what it does. We found the input into R, that was 0, and then it finds the R value at that 0, and then it multiplies it by delta x. M times the change in x. And so what is that? That's a little bit of accumulated weight due to the first completed interval. Okay, let me stop and see if you follow. Do you follow that? What happened? Please. Yes. On the graph, what is what I just put a box around on this accumulation graph? Do you see what that is? So what we found is the accumulation due to the first interval. Where does that show up in this graph? Okay, but where do we get that value? We came up with a value, 0.075. It's the y-axis of this point, right? The y value of that point right there. At the end of the first interval, we've accumulated a certain amount. That's what we just calculated. The constant rate times the change in x, 0.3, gave us 0.075 hundred pounds. Which would be that y value right there of that at the end of that segment. Did that make sense? Okay. Interval 2, we already got the left side was 0.3, so then that formula will take r of 0.3, and we estimate that from the graph. What do we estimate that from the graph? Quick and nice and loud. 1. Awesome. Okay? Therefore, then what the formula does is takes the r of 0.3 times delta x equals 0.3 hundred pounds. Okay, into the third interval. What does the formula do? It calculates the left side of the current interval, 0.6. It takes the rate at that value, r of 0.6. Estimate is, nice and loud and quick, 3. Awesome. And then it takes that rate, that constant rate for the whole interval, times delta x again. dy equals 0.9. Last interval, fourth interval. We already found the x value at the left side. R of that is r of 0.9. Estimate from the graph? 4.75 times 0.3. I want to get this. Nice and loud. 4.75 times 0.3. 1.425? Someone else get that? So what did we just do? We found the bits of accumulation for the 4 completed intervals. The way that the formula did it, right? The way that the formula did it. We're not done. We're not done. Let's show that we get about 350, okay? Now what? Partial interval. Partial interval. It does r of left of x times x minus left of x. So what was left of x? We already found that. 1.2. So it's going to do r of 1.2. What's x minus left of x? That's our dx, right? It's not a full interval this time, so it's times the 0.2. What's our estimate for r of 0.2 from the 1.2 from the graph? 4.25 times 0.2. Nice and loud. 0.85. Someone else get that? There's our little accumulation from the current interval, calculated by r of left x times x minus left x. Okay, now what are we going to do? What does the formula do? It sums up the accumulation from the completed intervals plus the little amount more from the current interval. So do that. Sum up these. We're expecting what value? About what? 3.5. We're expecting about 3.5 when we do that. So 0.075 plus 0.3 plus 0.9 plus 1.425 plus 0.85. I'm crossing my fingers, but it should be close. What is it? 3.55. Awesome. Yes, you can clap. And what is the units on that? 100 pounds. This is accumulated weight. So 100 pounds.